Assalamu alaikum warahmatullahi ta'ala wa barakatuh. Bismillah ar-Rahman ar-Rahim. Ladies and gentlemen, let's continue our tutorials about HAP cooling loads estimation. In this video, we're going to complete our project. We're going to talk about duct sizing. As you know, we finished the cooling loads and heating loads calculations using HAP. And the next tutorial will be about the energy calculations. As I said, it's according to my senior engineer Usama Atif. He uploaded the Arabic illustration of the energy analysis using HAP, and we're gonna talk about it the next tutorial if Allah wants. Now we're gonna complete our project. Here is duct sizing. So there are important things you have to know before starting duct design. The length of the duct should have be the possible minimum, the minimum length, and using the least number of fittings, elbows, and branches. This will decrease the cost of the project and the pressure loss. Okay. The minimum length, the least number of fittings, elbows, and branches will decrease the cost and the pressure loss in the duct to the minimum limit. Then the cost of the operation will decrease because you will have to install a fan that pushes the air, and if the pressure loss is the minimum, the fan power will be the minimum. So it's preferred to use round ducts, and also it is preferred to use round ducts over the rectangular ducts. Why? Because the pressure loss will be lower. At the round ducts, the pressure loss will be lower than the rectangular ducts at the same perimeter. And also it's recommended to use the aspect ratio, the length to the width, or the width to the length, to be 1 to 1. If you use the rectangular duct to be 1 to 1, and up to 3 to 1, and does not exceed 4 to 1. You can exceed 4 to 1 only in the industrial applications, not in the residential applications or the offices or places like that. Then here, just a minute, please. Okay. After determining the flow rate for every outlet using the HAP software, we draw the single line diagram like that. This is the single line diagram, and calculate the accumulated flow rates for every part. Here flow rate, and here flow rate. Okay, for every duct in CFM or liter per second, as you know, and for the section, and then assume an initial velocity of the air for the first section, the root section. And here this is a machine, suppose it's a fan coil, and here's the fan, and here is the main duct is AD. AD is the main duct. BE, CF, DG, and DH are branches. Okay, So we assume, according to the application, the initial velocity. If this duct is in residence, so the controlling factor duct friction here is the main duct, so the supply it will be 5 foot per minute, I think, and if it's a return it will be 4. And here if it is a branch duct, not the main duct, it is a branch duct, it will be 6 for the supply and 5 for the returns. Here or 3, so if it is residence, here apartments, hotel bedrooms, and so on. Here look at the industrial, the velocity increases due to we do not need to decrease the dB, the decibel. The velocity increases and the decibel level increases, and this is not a problem in the industrial applications. Okay, so you have to know is it 5 per foot per second or foot per minute. You have to know the number and the units. And here we have this single line diagram, and we have to size the ducts. Okay. And here is the we're gonna talk about the equal friction method. This is the equal friction method. This is the initial velocity, and here is the friction. We're going to talk about at first the MAP method or the manual method. Then we're going to talk about the duct sizing by the software program, the Duct Mate. Okay, so please have patience. Don't worry. This is by Angel Osama. First of all, here is the friction loss and the air quantity in meter per second, and then you will find the velocity in meter per second or foot per second or foot per minute. But here I think it's meter per second. It's according to the map you use. You have to use the latest maps. And here is the duct diameter, the round duct diameter. So this gray this gray zone, it is preferred to use the numbers that are included here, because it is the common, okay, or the popular area for sizing the ducts, okay. And the other areas you can use it, but in some kind of applications, okay. And this is according to the research and the experiments before generating these kind of maps, okay. So suppose that you have a flow rate here 200 liter per second air quantity, and then you have a velocity of we have this velocity 4 meter per second, okay. So 204, it will be here is 0.8 as the pressure loss, okay. This is for the first duct or for the main duct. Then at this point you can get the diameter. Where is the diameter? The diameter will be, it is 0.8, and the diameter will be this, okay. This here is the cross section. Oh, here this the connecting lines, or is the point, Okay, so it will be here, this point. Okay, it will be 800, I think. This 400, and this is our point. It may be 7. I'm sorry, it's not clear. So you get, so to sum up, you have air quantity and an initial velocity according to your location or your application. Then you get the friction loss that will be fixed, and we were gonna use it all the time, 0.7, and then you can get the diameter. Okay, so for the next sections, the friction will not be changed, it will be fixed. So we're going to use 0.8 as friction loss, and the velocity has to decrease due to this method when the flow rate decreases. Okay, when the dimensions of the rectangular duct fuse the rectangular duct, when the dimensions of the rectangular duct change, sorry, there's no S here, we often fix one dimension and changes and we also change the other until we reach to the aspect ratio that approaches from 1 to 1. And it doesn't matter changing the width or the length, you have to change one of them or change two of them. It's according to your design, no problem, but the important thing is to reach 1 to 1 or 2 1 3 1. So it's preferred to do that. Okay. So here the friction loss is in Pascal per meter, and we have 0.8. This means that if you have a duct 10 meters, you will lose 10 times 0.8. So you will lose 8 pascals without any fittings. So if you add fittings to the duct, you will increase the losses. Okay. So we got the diameter, the D of the duct. So you open this chart, and you this is the round diameters, and here is the length of the side, okay, of the duct, the rectangular duct, and here is the other side. You can use the diameter if you here suppose you got this diameter from the previous chart, just for example. You can use the round if you wanna round, but if you will install rectangular ducts, you have to get the dimensions of the rectangular ducts. Here is the length, and here is the other side. So this is the round diameter. So here is the length, 225 millimeters, and here is the second dimension, or the width. So it will be 1,300 millimeters. Please, you have to choose the dimensions that you get the aspect ratio 3 to 1, 2 to 1, or 1 to 1, and you have to know exactly what is the ducts that, or the dimensions that are provided with the companies. Okay, and you have to read more catalogs, or to know what's going on in your country in this field. So you have to select the appropriate duct if you cannot reach the required diameter, you have to choose the next larger diameter, and get the length and the width of the rectangular duct, and you have to check out the aspect ratio. Okay. Then, as you know, here is B times H, millimeter, 1000 times 250, and here is the equivalent diameter. This is the round and this is the rectangular, and here is the 0.21, just for example, and here is the initial velocity 3, and here is the airflow liter per second, here the section AB, and then here is the section AB, here is the section AB, and then section BC, 150 liter per second plus 150 liter per second plus 220 liter per second plus 100 liter per second is the total flow rate. Okay, that will be provided with AB. Okay, so please take care of this. This is the total, then it decreases after providing this branch with 100 liter per second. So BC will be the total minus 100, 520. Okay, and so on. You have to take care of the B times H, the aspect ratio, and the suspended ceiling height. If the architectural engineer tells you that you have a suspended ceiling 30 centimeters, so your duct, your B times H, shouldn't exceed 20 centimeters due to the insulations, due to the electrical wires, and so on. If you cannot reach the recommended height, or the suspended ceiling is 30 centimeters, and you wanna install, and you have, according to the calculations, you have to install P times H more than 20. Suppose that the length is more than 20 centimeters. You have to ask the architectural engineer to change or to increase the length of the height of the suspended ceiling to 40 centimeters or 50 centimeters. Then you can install your rectangular duct. Okay, you can read about rectangular ducts and see how we change one side and fix one side. Okay, and here is the equal friction method. You fix this, and you have the airflow, and you have always this. Okay, so you get the diameter, and then you get the velocity, and you get the equivalent diameter if you wanna use rectangular duct. If you do not need to use rectangular duct, you have only to choose the this diameter, and that's it. And here is the map that we have. Notice that this is the height and this is the width. The height, as like I said, it's according to the suspended ceiling height. So it's 25 centimeters. You have suspended ceiling 30 centimeters or 35. You assume first height for this, and you get the other side from the table. Then you fix this, and so the method here is you check out the other diameter, and at the same height we look at the second dimensions. The flow rate decreases, so here's the volume will decrease. Okay, and we have to fix this and change this, fix this and change this. It's up to your design. It's not a rule. You have to follow the best for your design. You may change both, doesn't matter, no problem. But the very important thing is to get the aspect ratio that does not exceed 4:1 or 3:1 in the residential or the offices, not in the industrial applications. The industrial applications may reach 12:1 or something like that. Okay, ladies and gentlemen, now we're gonna talk about the software program DuctMate. But before starting it, like I said, if you get a number or a point under this area or over this area, you have to take care of the pressure loss. If it's very big or it's large, you have to make a compromise between your selection and the cost. You have to recalculate everything and to check out everything to not be in a trouble or not be in a problem in the design process. Okay. Okay, let's open DuctMate. Okay, here is our DuctMate. Here file, open, save, restart to defaults, report preview, edit, calculate, roughness settings, units, metric or imperial. You can choose what you want, and metric, and with like a compact line. Okay. Like that, and here are the units. Okay, and here are the help, contents, register, about. Okay, ladies and gentlemen, this program takes into account the pressure or the head. Here the pressure and the attitude, because it affects the density of the air. So the design of the ducts will be affected. Click on this to locate your location. Here, South Africa, United States, Australia, Africa. Here's Africa. This is my location, Cairo. Here this is latitude, longitude, time zone, altitude over the sea level. Okay, and the dry bulb and the ranges. Okay, accept. So that's it, accept. And here the average temperature, click on this. Here is the average temperature inside the ducts. So you have to know the supply duct may be 12. Okay, and you have to enter the wet bulb. So it may 13 or even 12, no, 11 or 13 and 12. No, I'm sorry. 013, and is here the wet bulb is 12 inside the duct, and you have to enter 2 at least. You may enter the dry bulb and the relative humidity, or the wet bulb and relative humidity, or the dry bulb and the wet bulb. Okay, so this is the dry bulb and wet bulb. It's okay, and relative humidity is around 90%. So that's it. Okay, and here is the duct roughness. Duct roughness actually smooth at the PVC. It's very smooth. I think it may be used also if the duct is glass, I think, and medium smooth if it is a galvanized sheet metal, especially the newest if you buy the newest galvanized sheet metal from the company, not the old. Okay, changing medium, smooth, and smooth, notice here, and the average is the old galvanized sheet metal, but it's not common. And medium roughness. Okay, medium roughness, I think it is when the material that you use is slightly rough, like if you have a fan coil and the first 4 or 3 meters of the duct that connects to the fan coil, we use a lining material. This lining material is for lining the duct to decrease the level of the sounds or the noise. Okay, so this material is some kind of rough, so we use here medium rough, and rough if the duct is a flexible duct. Okay, supposed to that changing this roughness changes the pressure rate, but I do not know what the problem right now. But it's to you. If you change this, you have to know that the pressure rate changes. Okay. Okay, we suppose that we are gonna use galvanized sheet metal, medium smooth, and the pressure rate according to our example here. Here is the airflow, 600 liter per second. So this, right click and use liter per second, and here is 620. Okay, and the velocity 3 meter per second, the air. Okay, notice that the pressure rate is 0.2. it is almost equal to this number that we got from the manual method, from the charts. Okay, so this is the beauty of this software. In just less than 1 second you get the pressure rate. And here the velocity 3, not 300. This is 3, not 300. And here is the equivalent diameter. If your diameter, if you use a round duct, so 513, this is the diameter. If you will install a rectangular duct, the clear height is up to the architectural engineer, if you have a suspended ceiling 1 meter, you are allowed to use this height, but you have to know that this is it's around 55 centimeters. Okay, it's okay. And here the clear height, so divide this by this to know the aspect ratio. It should be within 3 to 1, 2 to 1, 1 to 1, and does not exceed 4 to 1. It's up to you. So here is the equivalent diameter. Look, 513. Yeah, in just 1 second. And look at this, 250. Okay, just about 982, but we did not find this in the standards, so we got the larger 1000. Okay, then this will be the same. Equal friction method tells you that, and then we will change this. Okay, and this is 0.2. Remember that. And here the round velocity. Okay, it's okay. And here the equivalent diameter. It's okay. And here is 250, and here is 842. So it's okay. The larger, it's according to our available products in the market. Then 100. It's okay. Look, 1.89. Here is 1.9, and the equivalent diameter 259, and here's 250 0, and here's 250. Okay. Here is I think 1.9, but here the program tells you here we go. Why? And here the aspect ratio is very good, so you can use this, and the equivalent diameter. Yes, I think this here is I think there is a problem here in this. Okay, so this is the clear width, 225, not 250 0. Okay, we do not need more, but it's according to the products or the width that is available in the catalog. Okay, so you can change this to the larger if possible. And here 300. Okay, 300. Look, 2.5, 391. Yes, here the equivalent diameter, and here 251 0, and look, 529, and here is larger. Okay, it is larger due to the available products in the catalog, and you are allowed to increase this width if this is not available. Okay, and so there is no problem here in the numbers. And 220, here is the equivalent diameter, 348, 347. Here is according to the chart, here according to the software, so you have to know what's going on. and what is the best. 250, and here 412. Here is according to the chart, according to the available in the markets, 450. Okay, then volume flow rate 150, equal fraction method 210. Here 2.1 meter per second, and equal diameter 3.2. okay, and the clear height, okay, and here is 305, here is 350. okay, no problem. This is the method of the chart, and this is the method of the program. You have to know the best choice, what's available in the market, and to know the medium, smooth or the average. Okay, the change of the pressure rate, but here I think that there is a problem, but it doesn't matter. What only matters is the pressure rate. You input it and make it fixed, and here you change the volume flow rate, and you get the round duct equivalent diameter after setting this for the first time, as we did. Okay, so this is the clear height, the clear width, no problem at all, and there is no problem between the two methods. Okay, ladies and gentlemen, this is the duct mate. It's very simple, very useful, and very quick. Okay, now we're gonna talk about the pressure loss in the fittings. Now we're gonna talk about static pressure calculation. So determine the worst path. It may be the longest path, or it may be the path that contains many fittings, elbows, filters, air outlets, dampers, and noise reducers. These devices increase the static pressure losses. Okay, so suppose that you have a balloon and it is full of air, and the pressure is completely static. Then you open this balloon, so the pressure, the total pressure actually is, so suppose that it's constant, and the static pressure will decrease and the dynamic pressure will increase, and if you add the static pressure and to the dynamic pressure, it is fixed. It equals the total pressure. And here is the duct. Here the static pressure. You have to calculate the static pressure loss to know what exactly you have to push the air until it reaches the longest path or the worst path. So if a section's length is 10 meter, a rectangular duct 10 meter, and the pressure loss is 0.2 Pascal per meter, then the total pressure is 0.2 times 10, it equals 2 pascals as static pressure loss. This is for the rectangular duct, and for the filters, the other devices, noise reducer, can get it from the catalogs and add them. And for the other here, for the fittings, actually you have two methods. From the software program HVAC Duct fittings database, or from this equation, delta P equal the constant times Vp. Here is the delta P, the static pressure drop in the in pascals, and see if the constants according to your case. You can find it in this Magna HVAC system design. in the Appendix A and or in the chapter F21 duct design for in ASHRAE 2009 or the latest ASHRAE fundamentals. Okay, and VP is the pressure velocity. Okay, plus the pressure here, plus the pressure, and it's half rho v square. V is the air velocity in meter per second, and rho is the air density, and VP equal 0.602 times V square. So you can get the delta P by calculations. You can make it, but actually we use ASHRAE duct fittings database. So let's start. Here we can see that the supply, if this duct, if this fitting is installed as supply fitting, okay, or return fitting, or common. It may be used as a supply or a return. So here the round or the round plenums exits, transitions, junctions, diverging, T-junction, non-conical branch. So you have to determine what you wanna, and here prefer the oval duct, and the common, round, rectangular, flat, oval. And in here junctions, T flat, junctions here double Y, and many things. You can find many things. Here 90 degrees, 45 degrees. This is the T junction without vanes. Okay. And here the rectangular, this and this. Those are the most common fittings. Okay, this is T, and here is angular. Here the double Y, but it is not recommended to use this these junctions at all. Practically it is very difficult to install this junction as a fitting or as a junction, because you will find that it is very difficult to distribute the air to the other ducts. And here okay, let's take this example. So let's input this data. Here the height will be click on project and call this references, and here the units SI, Okay, and here 1000. Notice that this is the height h. This is the height h of the main duct. Okay, and the width, this is the width. Okay, and this is the width of the branch, then the width of the branch WB is 250, and the width WS of this after the branch. Okay, WS 850. Okay, and here the flow rate QC, this is the total flow rate 620 as our example, and here is flow rate 100 QB at the branch, here 100, and there's the density. Okay, after finishing this, please click calculate, and here is the pressure drop in the branch is 2 pascals. This is the branch pressure loss. This is the important number here. Here the velocity, pressure, VP here as like I said, and loss coefficient. This is the C, and here is the pressure, branch pressure loss 2, and the main duct. Here the velocity and the velocity and everything, and here the number. This is the important number. Here is the main pressure loss is 0. So what is this? Suppose that here is the branch, and we assume that the worst sorry, not the branch. Here is our single line diagram, and we have A, B, C, D, G. We suppose, or we assume, or we guess that this duct, this main duct, and up to DG is the longest path and the worst path. Okay, so and here, so and for BE and ABE, the loss is 2 pascals. What does this mean? Suppose that you have a fan and it pushes the air at 20 pascals. Okay, then after reaching AB, after the air enters A until it reaches to B, the losses are 2 pascals. So the pressure here is 18, and after entering this branch, the losses is another 2 pascals, so we have now 16 pascals. And so 20, then 18, then 16, then 2 pascals after reaching E due to this branch, and so we have now 14 pascals, and there are 10 pascals losses due to this outlet, so we have 4 pascals only. So here is 20 pascals, and the air will enter this room or this zone with 4 pascals. Now let's continue here. Here is 18 pascals, and the program tells me that the losses here 0. Okay, 0. So 18, then 18, and due to the distance from BC, we lost 2. Okay, and here we got 16, and then 1, so we have 15, and due to this branch we lost 5, and until we got to this we got 10, and we have 10 pascals as losses due to this outlet. So the pressure loss or the air will enter this room with 0 pascals. It means that the air enters this room at 0 pascals. So this means that this is the longest path, and it has friction more than this branch. This is the main duct and longest path here, and we predict that the losses will be more than this branch, and this is what happened. The air entered this room with more pressure, it's 4 pascals, but the air enters this room with 0 pascals. Okay, so what happens in reality? Here is a single diagram. This is just a theoretical diagram. We suppose that this zone is 150 liter per second, and this room is 100 liter per second. But actually, due to the air that enters this room with 4 pascals, this amount of flow rate will increase in reality. It will maybe reach 120 liter per second, and due to the losses in the main duct and due to the fittings, this 150 liter per second, it may be in reality 130 liter per second. So in reality, we have to know that it is very complex, more than the single line diagram, and you cannot distribute the air as the single line diagram, due to the friction, due to the pressure losses that we can predict, that you cannot predict. So what is the solution now? If you predict that this is the worst path, A, B, C, D, G, so you can take the main pressure loss 0, as we said, and this is obvious because it has many friction and many fittings and many losses. And in reality, due to these 4 pascals, there is more than 100 liter per second will enter this room, and we do not need this. Okay, we need the 20 liter per second to be added here, because here the amount of the flow rate will be 130 liter per second. So what we have to do now is to install the device that controls the flow rate here, that decrease the pressure by 4 pascals. So the air will enter this room with 0 pascal, and also the air here will enter the room with 0 pascal as regular, okay, as we calculated it, or as we predicted. and it will be the other 20 liter per second will not enter this room. It will continue in flowing in this duct until it reaches this room. Okay. Again, to sum up, suppose that we have the total pressure loss from A to G 20 pascals, and from A B E 18 pascals. So we have 2 pascals more here. This means that the flow rate that will enter this room will be more than 100 liter per second, and here will be lower than 150 liter per second. So what we have to do in reality to install a volume control damper here to decrease the amount of flow that is equal to 2 pascals. The more pascals that we need, that we have here, to make the total static pressure loss from A to E 20, and from A DG is 20. So we have at the end, as a result of this, the flow that will enter this room 150 liter per second in the single diagram and in reality, and here 100 liter per second in the single line diagram and in reality. Okay, ladies and gentlemen, this is my tutorial about duct sizing and the fittings and the static pressure loss. I hope it works with you, and the next tutorial, if Allah wants, we're going to talk about the energy analysis. So thank you very much. Wassalamu alaikum warahmatullahi ta'ala wa barakatuh.